My name is Leonardo Bautista. I will present the WordPackage 4, which is the tools and OS system software part of the eProcessor project. It looks like I'm the last obstacle standing between you and lunch, so I will try to be as brief as possible. Okay, let's go. So the WordPackage 4 is basically the word package that tries to communicate between everything that it was presented at the beginning on the hardware side, and then the applications that Luke just presented a minute ago. Okay, so the intention here is basically to provide, first of all, a lightweight Linux kernel for risc-v with an OS operating system and the environment for the eProcessor to work well. Now there are different optimizations and optimal functions that we can look for. For example, of course, we want high performance, but we also want energy efficiency. And this is important for us for several of the use cases that it was presented before. One of those was this drone use case, in which the idea is that you can do detection of objects on a limited energy budget. So here we have to develop software techniques that allow us to leverage as much as possible of the resources of the hardware while still being very energy efficient. We also provide techniques for fault tolerance. So the idea is this, as Luke was talking about high performance computing, the idea is that if you were to use the eProcessor in a setting with thousands of nodes running high performance application, we need to provide resiliency for these kind of executions. Some of them are very, very long. Some of the trainings for machine learning are also very long. For the medical data sets, for example. And so for that, we need to guarantee that if a failure happens, we are able to restart from the last checkpoint and we don't have to re-execute everything from scratch. We also extend and optimize the eProcessor runtime libraries for supporting compiler technology to transparently exploit the features of the eProcessor platform. I will comment on some of these features that connect software and hardware and how they do transmit information between each other. So one of the advantages of working in a project like this is that you can do kind of some hardware software co-design, and that is what we are trying to do here. And finally, we are trying to develop performance analysis for risc-v and some debugging tools as well. I'm going to present that as well. So just to start, we have this asymmetric multiprocessing. Basically, here the idea is that we have this shared memory scheme you have the interaction between different OS environments coexisting on the same system on chip. So you have on one side the host with the ARM processor, and on the other side you have the risc-v accelerator. And so the idea is that they have a asymmetric multiprocessing here, and we are currently demonstrating this on an early generation FPGA. Here you have basically the different layers for the remote processor messaging. So you have the physical layer with the shared memory interprocessor interrupts. You have the data link layer with the risc-v, and the transport layer with the remote processor messaging channels and endpoints. On the efficient resource management, you have what we are trying to develop here is, as I mentioned, we need to be very careful about energy consumption. And so the idea is to develop an energy-aware scheduler that manages per task DVFS, so dynamic voltage and frequency scaling, and also dynamic concurrency throttling, okay, and core selection as well. And this is one of the things that is being currently integrated into the LLVM OpenMP. So one of the good things about this is that we are not only doing this for the eProcessor, but several of the software things that we are developing are currently being integrated into LLVM OpenMP, and so that other projects can also leverage these things. Now, right now, the extensions for the accelerator system are being developed. Now, for the support of fault tolerance, what we are trying to do is, so we have two things. First is the communication between hardware and software, as I mentioned before. So here the idea is that when you have error correction and error detection in the hardware, we are trying to provide data counters that are giving information to the software about the status of the system. So, for example, if the node is, for example, too hot and it starts to see too many bit errors corrections, we can release this data to the runtime, and the runtime can take actions in order to adapt to the fault mode that the machine is operating on. So, for example, if we are observing too many errors, we can increase, for example, the checkpoint frequency dynamically and automatically to adapt for this period. Or if we later on we see that the errors start decreasing, we can automatically readapt the checkpoint interval or even the checkpoint reliability level in order to adapt dynamically to the observation of how the system is behaving, right? So for that, we use a multi-level checkpoint library that is developed at BSc. It's called FTI, that offers 4 levels of reliability. You have the most reliable level is checkpoint on the file system, and then you have different erasure codes that allows different levels of reliability and performance trade-off. And so dynamically, you can adapt which level you want to use and which frequency you want to use for each one of these levels in order to cope to the number of errors that we are observing in the system. Another thing that we are doing is adapting the fault tolerance schemes for machine learning applications. So, for instance, when you are working with TensorFlow, you can checkpoint your training. But most of the times, these checkpoint schemes are developed for kind of a single node training when you were running a small model with a small data set, and then that works fine. But if you are looking at training into massive data sets in which you're training with many GPUs and this running for many hours, then the checkpoint scheme that you have in TensorFlow is not as interesting, is not as fast as the techniques that we have already developed in high performance computing for checkpointing. But there is some difference between high performance computing applications and machine learning applications. One of them is that in machine learning, when you are training a model, most of the nodes have basically the model at the end of the epoch, right? Because you have to synchronize that assuming you are doing data parallelism, which is what most of the times we are doing. But then in that case, you can actually parallelize the way you checkpoint because all the nodes have the same data at the end of an epoch. And so based on that, you can parallelize the checkpointing in order to speed it up and to decrease overhead. So we implemented this into a TensorFlow. We compared it with TensorFlow, and we implemented this into a new library that we call PFTI. And well, here is a comparison of how the accuracy evolves with a normal execution, an execution that does a recovery with a TensorFlow, and now also an execution that does a recovery with our library. And basically, we see kind of the same accuracy for all of them. So this is just to prove that that our checkpointing scheme is providing the right reliability level after a restart. But more importantly is this comparison about the performance of the scheme that we are developing. So this is a comparison with TensorFlow. Previously, there was a question about whether we are comparing our tools with what exists. In case of the software, we already have some results like this one. So what you have in the blue bar is checkpointing with TensorFlow, and this is the overhead that is causing. So high is bad, low is good. And we compared it with 3 techniques that we develop. We call it pickle part, least part, and least part weighted. We don't have the time to explain which one, what is the difference between them. But they basically do different types of optimizations about the way the data is serialized and the data is checkpointed. And we see that we actually gain over 50% improvement in comparison to TensorFlow. All right, we also work in compilers and runtimes. Here, the idea is to extend the LLVM risc-v vector support to cover small data types like integer 4, integer 2, and 8-bit floating point. Of course, this is very useful in the case of machine learning, where you can actually run models with small data types. This was already presented in the hardware part, that it is part of the hardware. And of course, we need to extend the LLVM support for that in the software side. Now, we also have deadlock management, but I think Nahir already presented this, and I don't have time, so I'm going to run over it. And finally, we have the computation of loading of off-chip CNN accelerator. So basically, here we have a convolutional neural network accelerator that runs side by side with the eProcessor. The accelerator is basically a two-dimensional systolic array generated for different FPGAs, right? And we have chip-to-chip link between the eProcessor and the FPGA. And so what happens is that some layers, some convolutional layers are offloaded to the accelerator, and for the rest of the part that is more sequential can stay in the processor. Now, for the programming and execution, basically you have the normal CNN training and quantization with TensorFlow and Keras. There is an API that controls all this on all the communications between the processor and the accelerator. Is basically you have C++ OpenMP source code compiled for the processor to deal with general application management and the other specific CNN layers. And so basically the idea here is that for some of the applications that Luke presented, for example, the ones regarding detection of objects, as well as the medical bioinformatic applications that require training of, detection of like the skin lesions and things like that. This kind of accelerator is going to be very useful for us because it's a convolutional neural network accelerator that is specifically deployed for these kind of use cases. And I think I'm a little bit over time, but I still have a couple of slides. We're developing these performance tools. One is tracing, so on the left side you have tracing, and the other one is sampling. And what we are trying to do, these are tools that have been developed at BSc. These are PAPI-like interface to read entry and exit of parallel runtimes, and we are trying to port this to risc-v performance registers. And we have been testing this on the C5 on matched board. And finally, we have the performance monitoring and debugging tools, Dynamo Rio. Basically, it's a tool that enables dynamic code manipulation, tracing, hardware simulation, debugging, performance analysis. So the idea is to port this into the risc-v, which is already ongoing. And for the eProcessor project, we want to use it for performance analysis and architecture exploration. And I think that's pretty much all for me. So if you want more details about the eProcessor, this is the website, and you can follow us on Twitter or on LinkedIn. So thank you for your attention.